Hi, I'm Chuck Gates, Manager of Buick's Field Service Engineering, and I wish to welcome you to this unit of the Buick Know-How Drivability Series. These programs have been designed and scrutinized by Buick Field Service Engineers. Many of you who have attended classes or worked with these engineers have learned that Buick Field Service Engineers know Buick products. From experience gathered by working on problem vehicles and talking with many of you, they understand the drivability complaints you face. Therefore, based on data gathered by the field service engineers, these programs contain valuable information to help you solve drivability complaints more efficiently.
This is the fourth in a series of Buick Know-How programs on the diagnosis and repair of drivability-related complaints on 1986 and newer Buick fuel-injected engines. The topic of this unit is drivability component operation and testing. Two releases in this series were, of course, on using scan tools to better read the ECM-PCM data stream when diagnosing drivability complaints, particularly when the problem we're trying to find is intermittent. But if we stop to think a minute, hopefully none of us grabs a T100 or Tech 1 ALDL lead right off when we begin the process of trying to solve a drivability complaint unless the vehicle is displaying a solid service engine soon light. The first step is getting the correct information on the repair order. That's where the service advisor's role becomes important. Then we begin to think through the problem. In planning our diagnostic approach, we develop an organized thought process that prioritizes the various possible problems that could result in the vehicle exhibiting the symptoms that the customer is experiencing. The thought process that we use is based on three general concepts: our understanding of how the systems and components work, our own personal history of what is most likely wrong based on past experience, and finally, a systematic approach to what you should check first, based partly on which of the possible problems is the easiest to diagnose or check first. When beginning a diagnostic routine to solve a drivability complaint, you should remember the basic systems that make an engine run: the fuel system, the ignition system, and the engine mechanical system, which can also be described as compression and valve timing. Today's engines could also be said to have a fourth area, that of the ECM-PCM and related sensors and output devices. Even though the ECM and related sensors are tied very closely to the fuel, ignition, and engine mechanical systems, they have actually become an area of diagnosis of their own. But this is not necessarily where you want to start your diagnostic procedure. This know-how unit deals with the basic operation and testing of these ECM-related components, but also includes some helpful information on the overall drivability theme. Included along with this know-how reference manual is another laminated handout developed by the Buick Field Service Engineers for your use. It's a general symptom diagnosis chart for use in diagnosing 1986 through current Buick fuel-injected engines. The chart contains 16 of the most common drivability complaints, from hard starts through open throttle stall, hesitations, sags, rough idle, and poor fuel economy. Under each symptom, there's a series of items that should be checked. These checks are organized to provide you with a systematic approach to diagnosing a particular symptom. The diagnostic routine is generalized enough to fit all engines and is not specific to a particular engine family. The chart assumes that you understand the test procedures called for, or will refer to those procedures in the shop manual. It's important that you realize that this chart is not meant to be all-inclusive. Not all possible causes can be listed under each and every symptom. For example, a restricted fuel filter could conceivably cause a rough idle, but a restricted fuel filter is not listed as a check for a rough idle, because a restricted fuel filter should first cause a loss of fuel pressure at higher engine speeds. Loss of fuel pressure should cause hot hesitation sag or low power complaints, along with the rough idle complaint. However, if fuel pressure is low and there's a hot hesitation sag or low power complaint, it's assumed that when the symptom diagnosis chart says to check for low fuel pressure, you check the fuel filter, along with fuel system components, such as the pressure regulator, to find the exact cause of pressure loss. Even though a diagnostic symptom chart cannot catch every possible cause of a symptom, Buick will start expecting you to follow this guide to give a more organized approach to drivability diagnosis. Your district service manager will utilize this chart when discussing the troubleshooting of a specific vehicle with you. If your district service manager instructs you to call technical assistance, the listed diagnostic procedures should be followed and the readings written down before the call is placed. And now, back to actual diagnostics. As mentioned earlier and shown in the general symptom diagnosis chart, to solve drivability problems, you must understand how the ECM-PCM and its components operate, as well as their relationship to the other three engine systems. In many cases, you start your diagnosis of a drivability complaint by actually running some systematic tests on the three basic engine systems. These include fuel tests, ignition tests, and compression tests. We've included a quick review of some of these system test procedures as an introduction in this manual. Ignition system tests were not included because the next know-how program in this series deals strictly with ignition system operation and testing. This know-how reference manual is here to help you with engine mechanical test procedures, fuel system testing procedures, as well as sections on common ECM-PCM input components and ECM-PCM output components. Included in engine mechanical tests are compression testing, cylinder leakage testing, and manifold vacuum testing. For example, manifold vacuum test procedures and results are explained. You should connect the vacuum gauge to a suitable manifold vacuum source. Then, with the engine running at normal operating temperature and the transmission in drive, you should see a steady vacuum reading between 16 and 22 inches of mercury. If the needle on your vacuum gauge fluctuates or drops back, it suggests that for some reason the individual cylinders are not drawing in the same amount of airflow. A fluctuating vacuum signal may be caused by leaky or sticking valves, a leaky head gasket, certain types of intake manifold gasket leaks, or an ignition system fault or fuel system fault. Each of these result in one or more cylinders not firing properly or producing its share of power. If you see a low but steady reading, it may be caused by late ignition timing or valve timing that is incorrect. A low but steady reading can also be caused by leaking piston rings or a leaking intake manifold gasket. If your vacuum signal floats or drifts, it may be caused by an extremely rich or extremely lean mixture. If your vacuum testing suggests a problem, it means more comprehensive tests. Tests like a cylinder balance test must be performed to pinpoint the exact problem. In the third section of the reference manual, there are fuel system tests. Included in the fuel system tests is the fuel injector leak test. You should check and make sure the injector retaining clips are in place. Next, you should remove the hold-down bolts. Now, carefully lift each side of the fuel rail, just enough so that you can see the injector tips. Then, with a jumper lead installed to the fuel pump test connector, check for drops of fuel building up at each injector tip. You should clean or replace any injector that leaks more than one drop of fuel in 1 minute. The fourth section of the reference manual explains ECM-PCM input components, more commonly known as sensors. It's important to remember that an ECM-PCM, as a computer, commands its output components based on what the inputs are telling the ECM-PCM. If an ECM-PCM controlled component is not functioning, it could be the component itself, the ECM-PCM, which includes the PROM or MEMCAL, or the inputs to the ECM-PCM. For each of the common sensors, the reference manual has a section explaining the theory of operation and suggested diagnostic tips. If you take, for example, the coolant temperature, the section starts with a typical wiring schematic. In the description of coolant temperature sensor operation, it's explained that the coolant temperature sensor is a negative temperature coefficient thermistor. In other words, the coolant temperature has high resistance at low temperature and low resistance at high temperature. With age and thermal stress, a sensor may fail during engine warm-up, causing the vehicle to stumble or stall while driving. Other unique sensor failures that can cause drivability problems are also listed. For example, you should also unplug the coolant temperature sensor and look for coolant leaks. Coolant has been known to travel up inside the sensor connector and into the wire. Eventually, it migrates into the ECM-PCM, resulting in engine drivability complaints caused by terminal corrosion. Coolant odor complaints in the passenger compartment could also be possible. The short sections of diagnostic tips for each sensor are not based on any one car, but are general enough to apply to all Buick fuel-injected engines. For example, if you connect the T100 to the vehicle and unplug the coolant temperature sensor, you should see a reading of -22 degrees Fahrenheit or lower if the ECM-PCM and related wiring are good. Likewise, jumpering the two terminals together should produce a reading of 266 degrees Fahrenheit or more. This is because with the circuit open, the ECM-PCM is seeing infinite resistance, which results in a maximum cold reading. With the terminals shorted together at the connector, the ECM-PCM is seeing virtually no resistance, which results in a maximum hot reading. The section on diagnostic tips contains additional service information. For example, if the coolant temperature sensor reading on the T100 is 176 degrees Fahrenheit instead of 194 degrees Fahrenheit at normal engine operating temperature, you shouldn't condemn the coolant temperature sensor right away. The faulty reading could be caused by a bad thermostat or by a leak in the engine cooling system causing low coolant levels. With low coolant level, the coolant may not contact the coolant temperature sensor, resulting in erroneous readings. Air pockets trapped in the cooling system can also have the same effect. You should also remember that the coolant temperature sensor often shares a ground with the intake air temperature sensor and the throttle position sensor. If the T100 readings for several of these sensors are off, you should check the ground circuit first. If you understand how the temperature sensor works, there is one other short test that you can use to check the coolant temperature sensor itself. If you connect a T100 or Tech 1 to a vehicle with a fully cooled down engine, the coolant temperature sensor reading and the intake air temperature reading should be within 4 degrees Fahrenheit of each other. If there is a code for a particular sensor, it's listed under applicable codes. For more specific tests for a particular sensor, you should see the tests listed under the appropriate code in the Buick Service Manual. The fifth section of the reference manual explains ECM-PCM output components. Here, you can observe the components that directly cause the drivability complaint, even if the problem is caused by faulty information the ECM-PCM received from a sensor. If you take the EGR valve as an example of an output device, the section starts with a general description of EGR operation and the various types of EGR systems used on Buick engines. The EGR system reduces oxides of nitrogen emissions. Oxides of nitrogen emissions are caused by high combustion chamber temperatures. Combustion temperatures can be lowered by adding an inert gas, a non-combustible gas like exhaust gas. The EGR valve itself is the main component of the EGR system. The EGR feeds small amounts of exhaust gas back into the intake manifold. The exhaust gas then moves with the air-fuel mixture into the combustion chamber. If too much exhaust gas flows through the valve and enters the combustion chamber, combustion is poor or does not occur. For this reason, the EGR valve usually only opens when the engine is warm and running at above idle speed. Since 1986, various styles of EGR valves and control systems have been used on Buick engines. Most throttle body systems are of the non-ECM control type, with the exception of the Roadmaster 5.0-liter and 5.7-liter engines. Buick Port fuel-injected engines, however, have used three distinct EGR control systems. On the 1988 and 1989 Regal, the EGR valve is controlled by the ECM. The ECM decides how far the EGR valve opens based on inputs it receives. Intake airflow or manifold vacuum and engine RPM are the two main inputs that control the amount of EGR valve opening. After gathering information from the sensors, the ECM sends a pulse width modulated signal to a voltage regulator. The voltage regulator controls EGR flow by regulating the current flow through the venting solenoid in the EGR valve. This pulse width modulated signal turns on and off many times per second. When the ECM is not commanding the internal solenoid on, the solenoid remains open, venting the EGR's internal vacuum to the atmosphere. On the other hand, when the ECM commands the internal solenoid on, the solenoid closes and the amount of vacuum applied to the EGR diaphragm is increased, raising the EGR valve farther off its seat. The section of diagnostic tips for each output component is for the most part not based on any one engine. Instead, diagnostic tips are designed to isolate the complaint. However, using the EGR valve as an example again, we will key in on some diagnostic tips specific to a certain style EGR valve and control system. Some drivers of vehicles with a 2.8-liter or 3.1-liter engine have complained of an occasional engine stall, sag, hesitation when accelerating, or a chuggle at steady throttle. While you know there are lots of components that can cause these problems on the 2.8-liter or 3.1-liter engines, let's look at the EGR system. To check the EGR system, begin by blocking the front wheels and setting the brake. Install your Tech 1. Start the engine. Warm to closed loop status and shift the transaxle to drive. Using custom data pairs, call up exhaust recirculation percent and EGR position. Now, you should slowly accelerate the engine while watching the data pair. There should be no change in EGR position until exhaust recirculation percent reaches at least 24%. The opening point specification for the solenoid valve is 24 to 39%. If EGR position changes with a 0 to 23% duty cycle, the solenoid valve may not be venting enough vacuum. You should remove the EGR filter and repeat the test. If EGR position does not change with a 0 to 23% duty cycle, replace the EGR valve filter. If the EGR position still changes, the EGR valve probably needs to be replaced. If the EGR position does not change, even with a 24 to 39% duty cycle, the solenoid valve is not functioning. If the ECM wiring and connectors are working properly, the EGR valve should be replaced. Some 1987 models contain EGR valves with bad position sensors. If the EGR position voltage changes with a 0 to 23% duty cycle on these vehicles and the EGR filter is already removed, slightly accelerate the engine again while touching your finger to the EGR valve diaphragm plate. If the diaphragm does not move, reinstall or replace the EGR filter. If the diaphragm moves, replace the EGR valve. The last section of the reference manual is an appendix that lists problem areas and the necessary diagnostic tools to repair these areas. Problem areas on the chart are divided into ECM-PCM, ignition, fuel, and compression timing. If you remember from the introduction to this program, these are the 4 systems that make a modern engine run. The problem area chart lists the likely things that should be checked in the event that you have a problem with one of these systems. Various diagnostic tools that are necessary to diagnose these systems are also listed in a chart. For example, if you are diagnosing a complaint that requires a check of the ECM-PCM, you need a T100 or Tech 1, a DVOM, and T-pins to do a thorough job. This program was designed to show you how ECM-PCM components operate. With a better understanding of component operation, you can diagnose complaints with a more organized approach. And don't forget to use the laminated Symptom Diagnosis Guide to further focus your diagnostic approach. Because an organized approach to drivability complaints helps solve these complaints and keeps Buicks and Buick customers on the great American road.